Yeah, welcome to this expert session on how to implement generative engineering. My name is Daniel, and since the beginning of April, I'm part of the customer success team here at ELISE, and I'm very excited to moderate this session today. For all the questions you might have, please use the Q&A button in the Zoom menu on the bottom of your screen, and we will get to those questions after the presentations are finished. Well, I think a lot of you work in product development or work with product developers, and you know the status quo of the many different steps and the different separate departments that are often involved in the process. And we have those isolated departments or silos. We have a lot of iterations, and at the same time, our environment is always rapidly changing, and it demands faster and faster innovation. And we at ELISE, we want to change this. And I'm glad to have Dr. Moritz Meyer, our co-founder and co-CEO, join us and later tell us more about our approach on how exactly we at ELISE want to change this. Hi, Moritz.
Hi, Daniel. Hi, everybody. Nice to meet you. And I'm very excited to have this session joining today.
Well, as I just said, just change your product development process. In theory, this sounds quite nice, but the question is, how do you do that? Our expert today has worked on developing and implementing new, more efficient digital seamless product development processes. Dr. Michael Riesener is the managing chief engineer at the Laboratory for Machine Tools and Production Engineering. Maybe some of you know it as the WZL of the RWTH Aachen University. And he's also the managing director of the Center of Systems Engineering. Hello, Michael.
Hello. Hi, Daniel. Nice to meet you. Hello, everybody.
Hey, thank you for joining us today, Michael. Could you give us a short introduction about yourself, about the CSE, and talk a bit about the motivation behind your work there?
Sure. Thank you very much for giving me the opportunity to talk to you, all of you today. As Daniel said, I'm Michael Riesener, and I have now been working for several years in innovation management, complexity management, systems engineering, and what we learned in the past years in cooperation with many different companies from different branches is that there are three steps taking place actually in the field of development processes. And the first one is the increasing shift of function fulfillment towards EE and software related functionalities. In the past we had the most function fulfillment has been done in mechanics, as some of you might have known or realized in the past. But today, more and more function is fulfilled in EE structures, and obviously this has an impact on the whole development process, which must be more interdisciplinary, must be more connected, more digitally connected towards over the whole product lifecycle and development process. The second one is the increasing view of previously isolated products. So we all know that in earlier times, product itself has been understood as a product, as a mechanical product. Today, we don't think about product, but about systems, about system of systems when it comes to, for example, in the agricultural area, about farm management systems, for example. And of course, this has also an impact on the methods, the tools that we use in product development. And this brings me to the last point on this page when it comes to tools and methods. And those have evolved over the past 30 years very drastically. And what we see actually is that there's a trend towards seamless engineering, towards simultaneous engineering in different areas, and obviously automated engineering. And that's why we are in a strong cooperation with ELISE, of course, as the Aachen University, because we think that ELISE is one very interesting solution in the context of algorithm-based product engineering, product development. And therefore, we are looking forward to further cooperation with ELISE and, of course, to the discussions that we have today. And the second step I want to show at the beginning as my first introductory words is that we as the Center for Systems Engineering, we have the idea and the vision to bring together industrial partners and interdisciplinary scientific expertise in this field of model-based systems engineering, in this field of digital connected engineering. And in our community, we have approximately 20 members from different companies like Kion, like MAN, like ZF, like Weiland, like some partners like PTC, for example, or Siemens and ELISE from the field of software-related products. And we all together work on the development of the new paradigm for the development process, which has to be automated and more efficient than today's development process. And therefore, I'm really looking forward to our today's discussion and your questions in the field of model-based systems engineering and generative engineering.
Thank you, Michael. Well, before Michael continues, I am interested in how the audience today compares to a benchmark the CSE did with a lot of different companies. So I will launch a poll right now. Please answer it on your screens. And to summarize, model-based systems engineering is an approach to product development that is especially useful to master the emerging complexity. And well, let's see how you poll.
That's going to be very, very exciting about what you think here in the audience and what is like the greatest success of model-based system engineering, because maybe so far it's just like a word that you have heard, maybe you have already implemented this methodology. So it's going to be a really interesting result here.
Yeah, because also as a research institute over the years at the CSE, you have gathered a lot of experience and studied this field extensively. So you must have found a lot of very effective levers that can be pulled for successful systems engineering. So it's interesting to see how that compares to our audience today.
Yeah, so we will have the result from the overall group that polled during our studies, and we can also then see how this differs maybe from our today's audience. So maybe.
Yeah, then I will end the poll right now and share the results. So maybe Michael, seeing these results, could you place them in the context of this consortial benchmark?
Yeah, that's very interesting to see. So approximately half of you have already implemented some aspects of MBSE. That's also true for the group that we interviewed during our studies last year. And also the greatest successes that you mentioned, for example, improving quality and the automation of repetitive activities. I think both of them are relevant for today's meeting because especially the automation of repetitive activities is something that ELISE also tackles with their solution. And what we have seen in our results. So if you just compare this to our result, we included some more answer possibilities. But the greatest successes that were mentioned by our group was also the enabling agile product development, which so you can understand it from that perspective that if you want to be agile, then it's not necessarily the main task to bring task boards and daily agile scrums, whatever meetings to the place, but to enable product development by technical solutions and by reviewing different iterative solutions. And the second one, improving quality at a very early time in the process, and the automation of repetitive activities and the unification of a functional and product view. I think these were all the answers that were also given by you. And we brought this in an overall context. So we considered different key learnings for the 3 parts: organizational requirements, consistent system architecture, and the technological requirements that you need for model-based systems engineer or for digital engineering in general. And yeah, so if you have any further questions on that, then please let us know during this meeting or also afterwards. When you don't have any questions at this moment, then I would switch to the last slide concerning the consortial benchmarking, where you also see different logos of the top performing companies. Maybe we have also representatives of those companies here with us today. So we have identified John Deere, for example, AVL, Bosch, Siemens, and ZF to be very good in that topic of model-based systems engineering. And what we also learned during that consortial benchmarking was that the integrated system model between the different departments is very crucial for the success of your development process. And you can see here in the middle that, for example, between requirements management, system design, and validation, there's a strong linkage between the different departments in the top performing companies. So if you're working towards a fully digitized engineering process, for example, with ELISE or with other partners, then you need to take care of that the consistency of the system model is clear and is given between the different departments, to not have a lack of knowledge between them. And yeah, I just can recommend this, and we can also go in talks about further key levers, but this was one very important one. Finally, our idea, and I think you would agree on some of the parts that I mentioned now. We are working towards the vision that we in the future we will have a document. We will have a way back from the document-based system development towards a model-based system development. So today, many of you or many of the companies focus on geometrically triggered processes. So you think about models that are sequentially used, for example, during requirements, during concept staging, and finally during validation. So we are working towards a start of production, and in the future, we believe that as software takes more and more function fulfillment in our systems of tomorrow, we believe that we have to have a paradigm shift towards a functional parameter oriented process. So we need to model the whole product life cycle. We need to manage models over the whole life cycle, and we also have a dynamic and continuous function process and data model updates. So this is also where ELISE can help, because in the very first part we can set boundaries for the optimization and the generation of solution principles. Later on we can validate them, and this can be one very important step towards a fully digitized engineering process together with different partners. And what we also learned during our our projects in the last years, that almost no company has a tool chain from only one software provider. So all of them have a combination of different standard products, and this is also a very good opportunity to implement solutions like ELISE or also other solutions in the terms of generative engineering, to have a fully connected line, but without very cost effective interfaces and interchanges. That's I think a very important point at this point of view here.
Awesome. And you talked in our pre-talk a little bit about the different levels, the hierarchical levels systems are made of, how you found them through your studies with your institute. Can you talk a little bit about that?
Yeah, sure. So we at first we need to discuss also with the companies that we work together with. We always discuss what's the main idea, the main task that the company wants to be solved. So is it the overview of the functional architecture of the product, of the system, or is it in terms of optimization of a given product system? And obviously, you can use these end-to-end systems to optimize product optimization, but you always need to define where you are at the moment. So there are companies that have the functional architecture, that have analytical models, and then it comes to more and more the integration of numerical models, combining requirements management, concept stage, and maybe validation. But other companies are at the very beginning, and then we start with building up the functional architecture for one specific hierarchy. And this is done then in different levels, as you mentioned. So we can focus, for example, on the very subsystem of the motor, for example, in this example, or on the drive area, or finally at the level of the end product. And we always go through the whole stage from the during the RFLP cycle, so from requirements over the functional structure towards the technical solution, and finally the end product and the validation. And by using this, we use models in a model library to combine them whenever we need them. And you can also go deeper and deeper. So if we model then the whole architecture model of the super system, obviously we can go deeper in the model of the system area or in the level of the subsystem, and we can answer the questions that the companies need to do at this point. And we did this not only in the scientific way, but also with big companies like OEMs, like mechanical engineering companies. We always follow the same structure, and this helps companies to some kind of have a systematic overview of their models that they use during the engineering process, because many of the companies start at the point that there are several hundreds of models in their company, but they are spread all over the engineering employees. Well, everybody has his own models in his own files or on his own computers, but they are not linked together in a model library. And that's what we do, for example, in our consortium with many producing companies, to bring together these models that they can be reused, and we can be more efficient in future development processes.
Yeah, talking about a lot of different models in different isolated departments, can you talk more? It's a bit about the generative engineering approach and how we try to solve this problem exactly.
Yeah, definitely. Thanks, Daniel, and also Michael. Thank you very much for this insight into the whole model-based system engineering approach. So what I usually get like as a feedback from the companies we are talking to is that the model-based system engineering approach is a very universal approach. So you have to rethink how you develop your products overall. It's a new thinking, it's a new methodology, it needs new processes, it needs new tools, obviously. And it all comes down that we are, as you said, Michael, we are not developing like the product itself, not the final part. We are thinking about functionalities. We are thinking about functions, about like interconnections between different areas, different perspectives. And of course, this is something where we as engineers, we are not used to. So we have been developed like classical tools, like the way like you would do it usually when you start from scratch. So I usually want to show like a linear process. So Michael, if you please can stop sharing it, I can switch over to my screen. That usually companies are developing their products in a serial approach. So this would mean like you start with your requirements, your load sheets, your parts that come from a different area, a different department. Maybe you already have some model-based system approaches on a very high level, but then you have a break and there's no connection to your development process on an assembly model or on a part. So then you go over like a linear approach, going for like construction models that are separate in PLM systems and not connected to the other worlds. Maybe then the next silo, as you named them, Daniel, is like the physics simulation, maybe the stress departments who are using their own models of maybe training data or having like the analysis done on their models. And it goes on and on. So, and the more complex the process get, and if I look back to your slides, Michael, we are talking about systems nowadays, not about products anymore. So this approach obviously was a very, very good approach, like maybe 20 years ago, maybe also like 10 years ago, but it will definitely not be a good approach in the future. So we have to rethink how we can more or less like, simultaneously get all those guys together to think about a system approach to connect all these tools, all these persons, all these processes into one environment, to think in functions and to think about a connected world. And we as ELISE, we think we can contribute to this approach, to model-based system engineering, because we think that maybe in the future, a development process on a part or assembly could look a bit like this. So we're starting with a very high level requirements and technical specifications that can come out of like a SysML tool or any other requirements management tools that are connected seamlessly to a overall connected engineering process, which we call like the technical DNA, because it's like a rule, a set of rules, a set of functions, how to create a completely connected and simultaneous approach for product development. And if we achieve to connect all the different software tools, all the people, all the departments into one environment, and if we are able to speak the same language, which is of course the necessary truth that we have to think about. We have to think about a language that the designers can speak, that the purchasing department can speak, that the stress department can speak. They have to understand themselves seamlessly. So we have to think about a universal language for product development in itself that is able to connect the cost evaluation, the multi-physics simulation, the CAD construction, the product design itself, but also like the functions and the requirements that come from a higher level approach and directly and automatically generate a final part of it. So this would be like a very nice situation in the future. And if we would achieve this, so if we really would be able to digitalize the whole way of a product development process, then maybe also like the question that Anand is asking here in the chat, what about like a digital twin in this context, might go into this direction. So if we would achieve of having the fully product development process digitalized as a function overall, maybe the final product then could also like be tracked on its production. So it could, for example, have like all the material properties or the manufacturing properties inside, because we have it stored like the development process digitally. But this, of course, is something which might be in the future somewhere. Maybe, Michael, you can give your insights on this topic as well. What about digital twins in these kind of model-based system engineering? Are there already some approaches?
Yeah, there are some approaches, because I think the system modeling is the very basic task that we need to have for the future, to have digital twins in place. Because only when we focus on the whole product lifecycle of a product or of a system, then we can analyze the data that we get from the field, for example, with respect to function, with respect to functionalities that have been used. So today there is a lack of knowledge, because we do not have a function-oriented modeling of the product by itself, and therefore the analysis of the using of the usage of the product does not fit to the requirements modeling, for example, or does not fit to the concept. So we are not able to learn from the usage of the car, or from the usage of the machine, for example, and therefore we need to have this modeling of this language, as you mentioned, that is understood by the requirements people, by the guys from the concept modeling, from validation, but also from people that understand how the product is used in the market. And when it comes to subscription, when it comes to digital twins, etc., the basic is always the basis is always the modeling, the correct modeling of the product. And therefore, we believe that MBSE can be the basic foundation for digital twin of the future.
Thanks, Michael. I totally agree. So there has to be like the databases on the same language, and this directly drives me to my next question. So what could be the universal language where all those guys talk the same thing on a level? And we deeply believe that this could only be like a programming language, because like our spoken language or the expert knowledge, it's not universal. So we have to talk about like a universal programming language where all these different tools could be connected. And for us, this is definitely something we are looking into it, and we're calling this algorithmic modeling, because we think that all the engineers, they do not want to write code. I mean, this is obvious, it takes too long. So we are like more on the way of like having a visual programming language with function blocks, like you can see here. And if you connect like multiple functions after each other, you can generate or digitalize a whole development process. And this could start maybe at the requirements management. This could start at the technical specifications, running over several processes, like, for example, the CAD construction, simulations world, cost simulation, controlling. All what is necessary in your development process could be like integrated in such a language. And if we are using the same language, of course, we can automate this whole process. And now things get interesting because we can speed up development. And I want to show you maybe like 2 examples from our past where we have implemented those kind of processes in the real world. Like the first one, I want to highlight a use case that we have been doing with Premium Aerotech in the aerospace industry. And I want to compare the classical approach, like you usually develop in this linear approach on the left side in this gray area here. And as you can see, this is like a typical image here. We're coming from a world where we have different design steps, lots of iterations, lots of software tools involved, silos involved, manual iterations. And of course, this ends usually up in lots of manual work, and we're getting slow and we are not achieving the best result. But if we are thinking on a model-based system approach, where we're only defining the functions, how the project or how the product should be like generated afterwards, we can do full automation here. And of course, this speeds up things, especially in this case, it was like an A320 part to 24 times more productivity rate. So this will cut down working hours by over 90%, which is kind of amazing. So the benefits that you also voted at the very beginning, being more agile, being faster, improving the quality, we can prove that we can achieve this on our everyday work. Maybe also very interesting and a very actual project that we are allowed to share for the first time is a project from the automotive industry that we have been doing with Hyundai. There's also like a nice ATZ article. If you're interested in, we can show you the details afterwards, but it shows the same picture. So if you are able to automate the process, you can end up with figures and KPI of saving 80% of your time, because you do not have to have the repetitive tasks being done. And in this case, I mean, it's an automotive part, so usually it's up to the top from the optimization degree, but we increased the crash performance by over 20% and saved roughly 50% of weight. So this is usually something which is not possible in a classical process, and it's only possible because we are like connecting all the different departments, all the different tools, and all the different functions. But yeah, let's see. I mean, PowerPoint slides are always nice to see. Maybe we also have some look into such a process itself. Daniel, what do you think?
Yeah, it would be interesting to see how this looks like realized in our software. So let's share this. So right now you can see our software, and I just put this slide of Michael in here because it will demonstrate very nicely how we approach this. So we have these different systems in hierarchies, and let's say we have here a nice car as our super system or end product. Our system itself is, for example, this wheel assembly, and we want to look at the subsystem of a steering knuckle, so this small part of the wheel assembly. So how do we approach this? Let's look at another slide. In the past, you would go geometrically and sit down and paint something and do some technical stuff. Tomorrow, we will approach this via systems of inputs into a subsystem generating outputs. So moving from geometrically triggered processes to parameter controlled processes. And if I zoom out, you can already see that it looks kind of exactly like this. We have some inputs on this side here, and we have some outputs on this side here. Let's go into more detail. On this side, we have, for example, a design space and a non-design space of the steering knuckle, which looks like this. This would be the design space and non-design space where the steering knuckle will be fastened, for example, through bolts to the wheel assembly. What we do with this, first, we need the material data, the load case data. We import all these information coming out of the requirements, coming out of the technical specification for the subsystem derived from the systems, from the hierarchy. We then go through the different steps in computing and creating this part. For example, pre-processing, simulating, reconstructing, and then at the end evaluating. In detail, we, for example, first mesh the imported components. We have a nice mesh here, and then go to define the rigid body elements for load application, for support application. And for example, here we can already see, again, this structure: inputs, some system, and outputs. And here our software works just like you would imagine. If I open this system, we have some finer steps in here. In this example, for the RBEs, we want to extract the reference geometries for the steering knuckle, where the loads are applied, where the supports are applied. This means we filter out these surfaces, and then we go on to define the RBE connector spiders on some master points, targeting all these surfaces here. And our output here are the finally defined RBEs. Going back, we can see this system is completely indifferent to what kind of design space or master point configuration goes into it. So this will automatically run on all kinds of design spaces where we have cylindrical surfaces and master points defining the connector spiders. So this is the beautiful configuration part of this approach, that it works just like you would imagine. And for example, you could just give parts or small systems like that to your subcontractors, and they would do the work for you, and you can just easily integrate it into your product development process. We then go on to define, for example, the boundary conditions, again, from the imported load case and load data in the beginning. And then we run a simulation to have these results for the different load cases. I'll just show this. And when we evaluate this model, we can define displacement responses and target displacements for our following topology optimization. The optimization itself optimizes the structure of this part, but as probably all of you who have done topology optimization know, the results are not that pretty. So this is in no way usable, what comes out of a normal topology optimization. So what you need to do right now is reconstruct that part. And from own experience, if you don't have nice processes after a topology optimization isomesh, it takes a lot of work and effort and a lot of playing around to get to a final result. What we are doing here is, for example, a quad remeasure process. Let me just, for example, go into this process again. So I open the included document, and you can already see, okay, this looks nothing like the topology optimization we saw, the result we saw just now, because we are using a voxel-based approach to rebuild the topology. Voxels are these small cubes in 3 dimensions. And we use that to rebuild the isomesh, turn it into a much nicer, smoother mesh, and then do some sorting and reconstruction, conversion operations, And as a result, again, our output here is a very nice looking quad mesh. And this mesh, as you can imagine, can be straightly used, if we go back here, to turn into a solid body. And our final part then looks like this. In this part, we also use the non-design spaces to put them in a Boolean union to our optimized part. So in the end, we have our final part with the clearly defined non-design spaces. We need to connect this part to the wheel assembly, and we can now go on to evaluate this part. And this evaluation, of course, means firstly a FEM analysis, so we can see, are the loads on the part correct? Is the part too light? Does it not hold the stresses? And we can also say, okay, this mechanical performance, depending on the different materials we have, leads to some KPIs. For example, the criteria for stress, deformation, and so on. Are they fulfilled? We see here, or okay, they are all true. We see the weight of the part instantly, and we can also see production costs and also the CO2 footprint, because we are working together with Fraunhofer IAPT. They developed a cost component here that places parts on a build platform of a AM machine. And let me zoom out here. It places them here, and through a design exploration, it also optimizes the configuration of parts and supports on this platform to get to the least material cost, the least price in euro per part. So this is very useful for AM processes. And for CO2, for this sustainability topic, which will become even more important in the future, we're working with Umberto to compute the CO2 that is generated per part produced. So if we look at all this, again, we built one part, and this part can be integrated into the whole assembly, and that integrated into the whole end product. And all of this process-based. So if, for example, we don't want to have this variant of the steering knuckle, for example, we have a smaller car we are building this for, we can just put in a different starting geometry of a smaller steering knuckle, and this whole process would just run through automatically and result in parts we can use and the KPIs we can use. So this is a very powerful process. And probably many of you will now have the question, this looks nice, but how can I implement this in my own organization? Moritz, could you and Michael maybe talk about how we are planning to collaborate with the CSE to help our audience get to this model-based systems engineering?
Yes, of course. Thanks, Daniel, for this introduction. Maybe before I start into the, let's say, the overall, how could I use this myself? There's one question in the audience from Marcus asking about our smoothing algorithm in here, if it's like a patented solution or if it's a publicly available code. So maybe I can answer this quickly in advance, because it's like in this area here. So it's like a code that is implemented in ELISE, so you can use it with our software. It's not publicly available, but it's also not patented. So feel free to use it and try it on your own part. So we are offering, of course, a try version where you can just test it out. It's a super nice algorithm. It's super powerful because it gives you exactly that, the missing part of reconstruction, something like a topology optimization or an ISO mesh, to a full NURBS model afterwards, which is crucial, some kind of the area. So yeah, the question is always, in theory, it all looks nice, and also live demonstration PowerPoint looks nice, but at my company, of course, I have like lots of departments. There's so much things to keep in mind. Maybe I don't even know where to start. So the question is, how do we actually get the things going? And I guess there are like, of course, two approaches we have to go. On the one hand, definitely, we have to look at the engineering itself. So we have to look at the things, at the use cases. We have to make sure that we get like the real KPIs or the real trust in such a technology from our management, from the sponsors. And of course, we can only do this with use cases, with real hard figures and facts and examples. But on the other hand, it's all about like a mind change in the people's work. So we have to rethink how we do engineering itself. And therefore, Michael and especially the whole CSE and ELISE, we are doing a partnership on this track to provide like those two worlds for you. And we call it like the road to generative engineering, because it's like the way to get things going. And as you can see here on my screen, it starts with your experience, with your team, with your experts. So usually we are having a group of, let's say, 2 to 3 experts who are in the product development. We have the management who is responsible for the product development processes in a different department, or even, it depends on the size of your company, obviously, a bit higher. So we have to have these both people involved, both stakeholders, because from our perspective, we need both of these worlds. We need to have the management, the theory and the methods, but also we need to have the engineers and the experts on board. And then what we're doing is we're getting started together, and we are dividing our streams in 2 main areas. And they're like the strategy area, and there's the engineering, the proof of concept area. Maybe Michael, you can say something to the strategy path, that it's like something you're leading here in this cooperation.
Sure, thank you, Moritz. Yes, the strategy part basically focuses on the integration on a management level of the solution of ELISE, and also the whole generative engineering idea into the development process and construction process of your company. So we start with an as-is analysis of the PDP as it is now. So you've seen some of the examples earlier from Moritz, how development, how calculations are done today. Then we will afterwards develop based on experiences that we did in other companies, also from our setup, to how a roadmap could be developed in your company, in your specific use case. For example, that you start in one product family, that you start with one specific functionality, that you start in one specific area or department, for example, and this and how the roadmaps develop afterwards. So what is to be done first, what can be done later on, etc. And finally, with the KPIs that we learn from the proof of concept that Moritz will point out later on, we of course integrate them into a business case at the end. So we do a plausibility check. We see, well, the proof of concept shows that we have a decreasing of development times, for example, by 40% in this specific point. And on the overall strategy, this would mean with 20 or 30 comparable products, comparable functionalities, we could save XYZ euros per year. This is done on the strategy level to also include the management level, which is very, very necessary, because we have this paradigm shift. This can be done bottom up, as Moritz will explain with the proof of concept, but it must be done top down as well to have the full impact.
Exactly, Michael. I guess there could be only like the 2 worlds coming together, being successful. And from our part, which we bring into the partnership, it's definitely about the proof of concept, as we are able to, of course, like train such a software like ELISE to your engineers, to your experts. And we are doing this in a like 4-step approach. So there will be like a first onboarding that the engineers get going in the software. Then there is like the starting point. We call it like the getting started phase, where we are learning to develop such a nice looking part like Daniel showed us a minute ago. But then, of course, we are going into your part. So usually there's something that we use as a first principle on your parts, because it's always nice to have this approach applied to your special project, to your special manufacturing techniques. Maybe it's not additive manufacturing. Maybe you are interested in having some more like serious production, like die casting or something. So we have to make sure that we're doing the proof of concept also on this technology. And then things get interesting, because we can come up with real hard figures. So we can measure how much time we are saving with this approach in comparison to the old process. And of course, these KPIs, they can be directly implemented in the business cases on a higher level to get like our outlook where we can reach with model-based system engineering in the ELISE in the future. But of course, also we have a screening. So Michael and its team, they looked into different parts and they analyzed which parts might be the next low-hanging fruits to enter with the technology. So what we are doing here in the last phase, in the transfer phase, is that your experts can do this on your own parts yourself. Of course, we support here, but we are able to also do the first transfer steps in order. And this two streams then come together into one management proposal, into a reflection of the results. And I guess it's a nice thing because you have learned basically the software. And at the same time, we can have like the outlook, what it's in for me, what is generative engineering more likely to do in the future to your company. So to sum it up, with this approach, it's definitely about a proof of concepts. We want to reach hard figures, not PowerPoint or slides. It's about the hard engineering facts. Of course, we want to train your people of doing it yourself, and you get the holistic overview about model-based system engineering, what it could mean for your company, where are the boundaries, what is not yet possible, what would be the low-hanging fruits. Of course, it's not like an eierlegende Wollmilchsau for everything, but you can try it definitely on the first steps and you get the outlook. And what for me, it's super interesting to see this strategic roadmap with the first steps. Where do I have to start today? And what could be in for my company in the future? Because I guess I've heard so many like people talking about this nice technology, but bringing this technology into reality, to really like doing hands-on engineering tasks with it. This is something which, is not quite often so far. At least I haven't seen it so far. And I guess here, together with Michael and the CSE, we have a nice setup of getting the things done together with you.
Perfect. Thank you, Moritz and Michael. Very interesting. So we're running out of time. I'm very glad to see that even though we're 3 minutes over time, most of you participants are not leaving us. So let's go to Q&A and just do one more question because Moritz was kindly answering a few questions earlier. So we have one more question from Marcus, who's asking, today there is the desire to do prototyping in additive manufacturing, yet uses a serial production method like casting. We could say also forging or whatever. How could these two or more methods come together with MBSE?
Yeah, maybe I can take this one as for us as an if we're thinking about in functions or in function blocks. So the question would be, what kind of function do I need to come up with a design for casting, for example? So how can I basically digitalize the expert knowledge on a design or also on the manufacturing constraints, on the costing, on the machine stuff? How can I capture this expert knowledge in a digital way to put it into a function? And from our perspective, what we have done in the past, for example, with welded sheet metal parts or something like this, it usually starts with interviewing your experts. So you're trying to ask those experts who have this expert knowledge in their like experience, in their stomach feeling, what is it all about? How could I transfer your knowledge into a rule, into a function that I can program in question marks? So this is like a thing that we have to do. So we are digitalizing the knowledge. And once we have digitalized it in functions, of course, we can multiply it. We can use it in different projects and different approaches. And we can do model-based system engineering with the expert knowledge that has been in the head of people before, isolated, now digitalized and available for the whole company.
Thank you, Moritz. So I will not hold you any longer before your lunch. So if you're interested in topics like this and want to know more, I will just launch a poll here and you can answer with yes. And then we will see who answered with yes and we will get in contact with you. And I will also post our email addresses in chat. So please feel free to get in contact anytime. And thank you, Michael and Moritz, for these super interesting insights into this topic and into how we, or how ELISE and CSE are working together to approach this. And thank you all for being here with us. and have a nice and productive week. Bye, guys.
Thanks everybody for participating.
Bye. Thank you. Take care.